Hello ladies and gentlemen, welcome back. This is Kamiti e-learning platform. Now, we are analyzing thermostresses and thermostrains. We got a problem here that says this. A copper flat measuring 60 by 30 millimeters is braced to another 60 by 60 millimeters mild steel flat as shown in the figure below. If the combination is heated through 120 degrees Celsius, determine 1. The stresses produced in each of the bars, the shear force which tends to rupture the bracing. That is question 2. Question 3, the shear stresses. The coefficient of linear expansion of copper is 18.5 times 10 raised to the power of negative 6 per degree Celsius. The coefficient of linear expansion of steel, 12 times 10 raised to the power of negative 6 per degree Celsius. Young's modulus of elasticity of copper, 110 giganewtons per square meter. Young's modulus of elasticity of steel, 220 giganewtons per square meter. So the two bars are braced together along this section, and the length of each bar is 400 millimeters. As the coefficient of linear expansion of copper is greater than that of steel, then it means that the copper flat will be, that is the extension of the copper flat will be more than that of the steel flat. But since they are blazed together, they have been welded together, the steel flat will tend to pull the copper flat, whereas the copper flat will tend to push the steel bar. But finally, they will, however, become stable at a certain position, and that position is position PP. We are going to begin with determining the compressive strain, because the copper bar will tend to be compressed by the steel bar, and the steel bar will tend to be extended by the copper bar. Therefore, the copper will be under compressive stresses, whereas the steel bar will be under tensile stresses. And the extension of the copper, bar. The extension of the copper bar, that is change in length in the copper bar, will be given by the coefficient of linear expansion of the copper bar multiplied by the change in temperature, that is T2 minus T1 and then multiplied by the length of the steel bar. This increase in length is the distance from Q to M. Therefore, you can say that the increase in length or the extension is from Q to M, which will be given by coefficient of linear expansion of copper times the change in temperature T2 minus T1 multiplied by the length of the copper bar. On the other hand, the extension of the steel bar, so extension of the steel flat or the steel bar will be given by changing length in the steel being equal to coefficient of linear expansion of steel times the change in temperature T2 minus T1 multiplied by the length. The increase in length of the steel bar will be the distance Q to N. That is the increase in length. It's increase in length. This is the pull due to the extension of the copper bar to the point of stability. So this is the increase in length of the steel bar, and therefore that is going to be Qn is equals coefficient of linear expansion of steel times change in temperature times the length. So those are the extensions of those two flats. The compressive strain in copper flat. So from there we go to compressive strain. Compressive strain in copper flat. In copper flat. And this compressive strain will be given by change in length of that is the changing length divided by the original length. And in this case, the change in length will be given by changing length is this distance P to M. So it will be given by QM minus QP. This is the change in length in the copper flat or the copper bar. So in this case, we got QM minus QP. So that is the change in length. Therefore, the compressive strain will be given by changing length, which is QM over the original length minus QP divided by the original length. But this QP over L is the common strain, because the common strain of the steel bar is also QP divided by L. Therefore, you can say that this QP over L is what? The common strain of the two flats, the common strain. So we are going to have the compressive strain being equal to QM over L, and we got the value of QM on this equation. Let's call it equation 1. So we are going to substitute it here. QM will be given by coefficient of linear expansion of copper multiplied by the change in temperature T2 minus T1 times L divided by the original length of the flat minus QP over L, and QP over L is the common strain, therefore E. So that is the compressive strain in the copper bar. This length and this one are going to cancel out. Therefore, we are going to have a compressive strain in copper bar being equal to coefficient of linear expansion multiplied by change in temperature minus the common strain. So let's call this equation 3. This one equation 2. Good. From there we are going to determine the tensile strain in steel. So we go to tensile strain in steel flat. Remember, I have said this, that the steel bar will be pulled by the copper bar, and the copper bar will tend to be pushed by the steel bar. Therefore, the copper bar will be under compressive stresses, the steel bar under tensile stresses. Good. So we are going to say this: the tensile strain in steel will be given by changing length in steel over the original length of the steel flat. So the changing length in the steel will be given by QP minus QN. So this is the changing length, N to P. So that is going to be QP minus QN. That is the change in length over the original length, which is L. We can separate the two by having tensile strain in steel being equal to QP over L minus QN over L. But we have said that QP over L is the common strain of the two flats. Therefore, we are going to have the tensile strain in steel being equal to the common strain minus QN. We got it here in equation 2, so we substitute it here. that is the coefficient of linear expansion of steel times change in temperature multiplied by the length of the flat. Divide this by this length here. Divide this by L. So this L and this one are going to cancel out. Therefore, ES will be given by E minus coefficient of linear expansion times T2 minus T1. So this is going to be our equation 4. Then from there, we are going to add these two equations, equation 3 as well as equation 4. So we are going to say this, adding equations 3 and 4. So when we add those two equations, we are going to have this. On the left hand side, we have the compressive strain in copper and the tensile strain in steel. Therefore, we are going to have this compressive strain in copper plus tensile strain in steel is equals to, here we have the coefficient of linear expansion of copper multiplied by the change in temperature. Let me write it as a change in T, that is T2 minus T1 minus E. We add it to this equation on the right hand side of the tensile strain formula of the steel flat. So this is going to be E minus the coefficient multiplied by the change in temperature. Therefore, this will lead us to EC plus ES being equal to minus E plus E, that is 0. So we are going to have the coefficient of linear expansion of copper into T2 minus T1 minus coefficient of linear expansion of steel into T2 minus T1. So that is what we are going to have. And then from there, so on this side we have EC plus ES is equals to coefficient of linear expansion of copper minus coefficient of linear expansion of steel, since these two brackets have got common item, that is temperature, into T2 minus T1. So that is what we are going to have. But we know this, the strain in copper will be given by stress in copper divided by the Young's modulus of elasticity of copper. And on the other hand, the strain in steel will be given by stress in steel divided by the Young's modulus of elasticity of steel, whereby these two stresses are temperature stresses. When we substitute these formulas here, we are going to have stress in copper divided by the Young's modulus of elasticity of copper plus stress in steel divided by Young's modulus of elasticity of steel is equals what we have on the right hand side. Coefficient of copper minus coefficient of linear expansion of steel into T2 minus T1. That's all we are going to have. Now, we have EC. We have the values of EC here as well as ES. So we are going to have this. The stress in copper divided by Young's modulus of elasticity of copper is 110. So this is going to be 110 times 10 raised to the power of 9 plus stress in steel divided by the Young's modulus of elasticity of steel, 220. So this is going to be 220 times 10 raised to the power of 9 is equals to, let me write the values on the right hand side down here. So is equals to the coefficient of linear expansion of copper 18.5. So that is going to be 18.5 times 10 raised to the power of negative 6 minus that one of steel is 12. So we got 12 times 10 raised to the power of negative 6 multiplied by T2 minus T1. The change in temperature is 120 degrees Celsius because the combination of these two flats has been heated through 120 degrees Celsius. Therefore, that is the change in temperature. So you multiply that by 120. When we add these two, the LCM of 110 and 220 is 220. Therefore, you are going to have 220 divided by 110, that is 2. This is going to give us 2 times the stress in copper plus 220 divided by 220, that is 1. So we got stress in steel is equal to 18.5 minus 12. That happens to be 6.5. 6.5. So 18.5 times 10 raised to the power of negative 6 minus 12 times 10 raised to the power of negative 6. That is 6.5 times 10 raised to the power of negative 6 times 120. Remember, we have an LCM. We have an LCM which is 220 times 10 raised to the power of 9. So we are going to multiply this, that is both sides, by that LCM. So on this side, it is going to cancel out. On this side, we are going to have 220 times 10 raised to the power of 9. So 2 stress in copper plus stress in steel is equals to, when you multiply 6.5 times 10 raised to the power of negative 6 times 120 times 220 times 10 raised to the power of 9, that gives us 171.6 times 10 raised to the power of 6. At this position PP, the point where, or the position where both copper and steel are going to be stable, no more pushing, no more pulling, the push in copper will be equal to the pull in steel at this point of compromising, the point of stability. So we are going to say this: at position PP, the pull in steel is equal to push in copper. Is equals to push in copper. And the push and the pull, these are forces. Therefore, the force that is pulling this steel is equals to the force that is pushing the copper, PC. And from this formula, we know that stress is given by rod divided by cross-sectional area. Therefore, when you make rod the subject, you are going to have stress times cross-sectional area. Therefore, the stress in steel times the cross-sectional area of steel is equals stress in copper times cross-sectional area of copper. Let's determine the cross-sectional areas. Cross-sectional area of steel is going to be 60 by 60. That is the mild steel. 60 by 60. Therefore, when you convert 60 to millimeters, you divide 60 by 1,000. That happens to be 0.06. Yeah. So the area of steel will be 0.06 times 0.06, which is going to be 3.6 times 10 raised to the power of negative 3. The cross-sectional area of copper, on the other hand, that is 60 by that. Convert to meters, 60 millimeters, that is 0.06 meters. 30 millimeters, convert to meters, 0.03 meters. And this is going to be 1.8 times 10 raised to the power of -3. Both of them square meters. So we got the area, the cross-sectional areas of the two. So when we substitute them here, we are going to have this. If we make stress in steel the subject, we are going to have stress in steel is equals the stress in copper times area of copper divided by area of steel. Good. The other part I'm going to write it here. So let me clean up this section. Therefore, the stress in steel will be given by stress in copper multiplied by cross-sectional area of copper 1.8 times 10 raised to the power of -3 divided by cross-sectional area of steel 3.6 times 10 raised to the power of -3. And this is going to give you stress in copper, that is 1.8 divided by 3.6 is 0.5. So this is going to be 0.5 times stress in copper. So we are going to say that, or in other words, we have this relation, stress in steel is equals 0.5 stress in copper. So when you come back here, we are going to substitute the values of the stress in steel with 0.5 stress in copper. And this will lead us to 2 stress in copper plus stress in steel 0.5 stress in copper is equals to 171.6 times 10 raised to the power of 6. So when we add 2 plus 0.5, that is 2.5 times stress in copper is equals 171.6 times 10 raised to the power of 6. Divide both sides by 2.5. 2.5. So this is going to give us the stress in copper to be 171.6 times 10 raised to the power of 6 divided by 2.5. That happens to be 68.64 times 10 raised to the power of 6 newtons per square meters, which can be rewritten as 68.64 mega newtons per square meter. Therefore, that is the stress in copper. On the other hand, the stress in steel will be 0.5 times the stress in copper, which is 68.64 meganewtons per square meter, which will give us what? Which is going to give us 34.32 meganewtons per square meter. So we have answered the first part of the question. Question 1, the stresses produced in each of the bar. Stress in copper and the stress in steel. Very good. Part 2 of the question, the shear force which tends to rupture the bracing. These 2 flats have been blazed along this section. So due to that push and pull, there is a lot of stress that is being experienced along this section, which we call shear stress. So we are being asked to determine the shear force that is resulting to that push and pull, which can result to the rupturing of, or which can result to rupture of these 2 components. So the shear force will be given by stress multiplied by cross-sectional area. So the shear force on the copper bar will be the stress in the copper bar times cross-sectional area of the copper flat. So in this case, we are going to have a shear force of, we call it SF, shear force. This is going to be stress in copper 68.64 times 10 raised to the power of 6 newtons per square meter multiplied by its cross-sectional area. The cross-sectional area of the copper is 1.8. So we are going to multiply this by 1.8 times 10 raised to the power of -3. And this is going to give us a force of 123,552 newtons, which in kilonewtons is 123.552 kilonewtons. So that is the shear force. When you use the steel, it will still be the same. That is the stress of that 4.32 times the area of 3.6 times 10 raised to the power -3. It will still give you a force of 123.552 kilonewtons, because both the copper and the bar are experiencing the same amount of shear stress along this section. Part 3 of the question, determine the shear stresses. Shear stresses. 1, 2, 3. Part 3. So the shear stresses. We are going to begin with calculating the shear stress in steel. And this will be given by the shear force divided by what we call the shear area. So shear area is the area that is experiencing that push and pull, that rubbing. And that is the section from this point all the way to that point. And for us to get the shear area, we are going to have the length of the bar 400 millimeters times the width of the steel flat. So in this case, 400 millimeters convert to meters, that is 400 divided by 1000, which is 0.4 meters, times the width of the steel flat, 60 millimeters convert to meters, that is 0.06, which is going to be 0.024 square meters. Therefore, that is the shear area. And therefore, the shear stress will be given by the shear force, which is 123,552 newtons divided by the shear area, which is 0.024 square meters. So when you divide 123,552 newtons divided by the shear area of 0.024, that is going to give us a shear stress of 5.148 times 10 raised to the power of 6 newtons per square meter. And this one can also be related as 5.148 mega newtons per square meter. Therefore, that is the shear stresses. The shear stresses. So, ladies and gentlemen, that's how I go about this. If it has been of benefit to you, please don't forget to hit that subscription button. And we are going to appreciate so very much. Thank you for your continued support. Let's meet in yet another lesson.